want to thank the organizers for having me here. So this is title is Universal Vertex Algebra Beyond W Trivial. This is joint with Thomas Kreuzig and my student Vlad Kovalchuk, finishing his PhD here. So first of all, universal vertex algebras are certain large vertex algebras that are defined not over a field but over some ring commutative. In this case, it's just going to be polynomial ring variables. They are useful for studying structure of W algebras. In particular, they're useful for classifying VOAs by strong generating type. So I'm going to review some earlier work with Thomas, and then I'll talk some of the middle aspects about such structures. Okay, so this is the same notation that was used in some previous talks. I'll just remind you. So G will be a simple finite dimensional Lie superalgebra. It has an even and odd part. W, K, GF will be the universal W algebra associated to G and some choice of nilpotent. Simple quotient I'll denote with a lower subscript. And for this talk, it's useful to replace the level with the shifted level, shifted by the dual constant number. So in my notation, W xi will always be WK with K equals xi minus H check. And then this will be the notation for the simple quotient. And if I have this principle, then I'll just drop that from the notation. I'll write it this way. Okay, so principal W algebras have certain dualities that I mentioned, because one of the things that we're talking about is a common thing. So the first one is Fagan-Frankel duality. So this goes back a long time. It says that the principal W algebra of G for simple Lie algebra is isomorphic as a one-parameter vertex algebra to the principal W algebra of its Langland's dual. And there's a certain shift of level. The product of the two shifted levels times the laicity equals 1. Okay, so this holds for simple Lie algebras. It also holds for OSP 1, 2, and here they have to replace this laicity by 4 in that case. Okay, so this is one of the dualities. And then the other one is coset construction. So first in ADE types, this is the way that it goes, and it's a generalization of the GKO construction of the Virasoro algebra. So G is simple and simply laced, then we can consider a diagonal embedding of an affine vertex algebra of G at level K plus 1 in VKG tensor L1G. L1G means the simple one at level 1. Okay, so we have this diagonal embedding, and CKG will be the coset of the image of this diagonal embedding. Okay, so this is isomorphic as a one-parameter family to the principal W algebra, and this is the relationship between the levels. And I should mention, too, that this is a statement about one-parameter algebras, but it also holds when the level, well, first of all, it holds for the universal algebras whenever the level is not a shifted level is not a negative rational. So when this K is not a rational number less than or equal to minus H check, this statement holds for universal ones. Also, if I pass to admissible levels, then the simple admissible level, admissible affine vertex algebra at level K plus 1 injects into the simple quotient on the right side, and this the coset of the simple one is isomorphic to the simple W algebra. Okay, so this.
What does the com mean again?
So com is it's the commutant or the coset. So this is a general construction in VOAs. If I have a VOA and I have a sub-VOA, the com of the smaller one inside the bigger one means all the elements that commute with that. It's always a sub-VOA. It's like the commutant in associative algebras, the centralizer. So in this case, if you take the coset of an affine VOA, this is simply the invariant under the Lie algebra G of T. There's an action of the Lie algebra, or the Katsbouti algebra, and you take the invariance under G of T under half of it. Is that cool? So it's a general way of getting new VOAs from old ones. The reason it's useful is if you have a VOA and a sub-VOA, the sub-VOA tensor that's commutant embeds conformally in the big VOA. So the big VOA you can think of as an extension of the product of those two. Okay, so anyway, so this is a coset realization for ADE types. For B and C types, there's a slightly different coset realization, which I'll mention. So here, if you take the affine vertex superalgebra of OSP12n, it has a copy of the affine vertex algebra of SP2n coming from this even Lie algebra. And if you take this coset, this is isomorphic to the B-type principal W algebra, but then this is also isomorphic to the C-type Fagan-Frankel. So unfortunately, there's no known coset realization for F and G types. It's an interesting question. I don't even think there's a conjecture. I maybe should mention also there's a coset realization of the principal W algebra of OSP12n, which I didn't write down. Okay, so the Fagan-Frankel duality and this kind of coset realization are actually two extremal cases of a more general theorem, which we call trialities. So let me say a few words about this. I'll mostly focus on type A because it's easier to explain.
Sorry, really? So in the previous slide, that nice theorem you said at the bottom.
Yeah.
You have another one for getting the W. What am I trying? Is there a similar thing where you swap the roles of the symplectic group and the special orthogonal?
I don't know of a. You mean to replace this with C-type?
Yeah.
No, not that I know of. No, this gives me. This thing is itself. I can write as a C-type algebra, just changing the level. But no, I don't know. Was that was the question?
Only there is one, right? If you take SP2n and these many free fermions, you have a diagonal action of OSP12n, and the commutant gives you again a W algebra of type BC.
Okay.
So it's kind of interesting because that's
Yeah. You're right. Yeah, this is in our triality paper as well. Yeah, there is a third type. Absolutely.
I can explain after.
Yeah, that's right. Yeah. I think I'm going the wrong way. Okay, so let me say a few words in general about trialities. So let's say that F is some nilpotent. We complete it to a copy of SL2 in my Lie superalgebra G. Let A be the centralizer of this SL2. So this W algebra will have an affine subalgebra with some shifted level psi prime of type A. The affine coset means the coset of this affine subalgebra. So for the story that I'll talk about now, I take the full affine coset. Later, the affine subalgebra may have several components. I may only take the coset of part of it. For now, I'll talk about the full affine coset. And sometimes we have to also take, in addition, the invariants under some group of outer automorphisms. So if A is either OSP12n or an orthogonal group, I have to take a Z2 invariant space as well. There's one case where I have to take the invariant under U1. So usually I'll leave this out of the notation, but sometimes it's not the affine coset itself that I care about, it's the orbifold of it. Okay, so trialities are isomorphisms between three different affine cosets for different Lie algebras or Lie superalgebras and different nilpotents as one parameter vertex algebras. And they are common generalizations of Fagan-Frankel duality, ABCD types, and coset realizations. Okay, so I'm going to try to explain more detail what the statement is in type A. So Thomas also mentioned this in his talk and gave an example. So this family of W algebras also has come up a couple times in this conference. These are what we call hook type or small hook type. So first I'll talk about the even ones. So I consider SLN plus M, and I have this decomposition. So there's I have a copy of SLN and a copy of GLM which commute with each other, and then the rest of this is the off-diagonal components. This is how it decomposes as a module for this Lie subalgebra. So my nilpotent I take to be principal in SLN and trivial in GLM. So this corresponds to the this kind of Young diagram, one big block of height n and then a bunch of trivial blocks. So this is my shifted level, and this notation just means this W algebra with this choice of nilpotent. Okay. So let me tell you some structural features of this. So these things you can read off from the decomposition of SLN plus M as a module for the corresponding SL2. So first of all, the affine subalgebras of type GLM, there's some shift at the level. It's sine M minus 1. So that just means Heisenberg times affine SLM. And then coming from this principal block, there are some even generators in conformal weights 2, 3 up to n. And then coming from these off-diagonal things, you have a bunch of copies of the standard representation these will give rise to some even fields in weight n+1/2. There's 2m of them. One group of m of them transforms as the standard representation of GLM, the zero mode action. The other group transforms as the dual of that. Okay, so this description works when n is greater than or equal to 1. If n is 1, then there's nothing in the n block. We just have an affine algebra. But when n is 0, these will be defined in a different way so that my statement holds uniformly for all n and m. These are not going to be W algebras. So if n is greater than or equal to 2 and n is 0, what I do is I take affine SLM at this level and I tensor it with the rank M beta gamma system. So the rank M beta gamma system has an action affine SLM at level -1, and there's a diagonal action, actually GLM at level -1, and there's an action of the same affine algebra, V xi minus m minus 1, on this tensor product. And then there's two more extremal cases. The 0, 1 case I just take to be one copy of the beta gamma system, and then the 0, 0 case I take to be just trivial. Okay, so there's a similar family of hook-type superalgebras. So the description is almost the same, except that I replace SLN plus M with SLN slash M. So it has the same decomposition as before, except that these off-diagonal parts are now odd elements of the Lie algebra. My nilpotent is principal in SLN and trivial in GLM, and slightly different notation for these affine superalgebras. One subtlety is that when n equals m, I don't want to take SLN slash n because it fails to be simple. I want to replace it with PSLN. So I get a simple W algebra. Okay, so the affine subalgebra is also of type GLM when m is not n. In this case where it is equal to n, there's no Heisenberg. It's just an affine SLN. We have similar description. We have some even generators that come from the principal block, and then these extra fields that transform as CM plus its dual, they're now odd in the W algebra. And then there's also some extremal cases that maybe I should mention. So that when m is greater than or equal to 2, this is similar to what I had before. When this component is n, I take affine algebra tensored with 2m fermions rather than bosons. So 2m fermions is the same as the BC system of rank m. And this has an action of GLM at level +1. So again, I have an embedding of the same affine algebra diagonally. And then there's a few more extremal cases. Maybe I'll talk about these. Okay, so now I can state the triality theorem in type A. So what I do is I consider the affine cosets. So maybe I should be a little bit careful what this means. So when m is 0, this is just the principal W algebra. That means that you just have this long block and there's no trivial block. So affine coset doesn't do anything. W algebra. When m is 1, then there's a Heisenberg. I take the Heisenberg coset. When m is greater than or equal to 2, it's a coset of GLM. And same thing over here. The only thing which is a little bit different is the case where n equals n. And so here, there's an affine SLN. But instead of taking just the coset, I also have to take a U1 orbifold. So when I pass from n slash n to, sorry, SLN slash n to PSLN slash n, there was a Heisenberg that I got rid of, but the action of the exponentiated 0 mode survives, and I have to take invariance under that to get something that belongs in this family. Okay, so these are my objects, the C's and the D's, and the theorem is that we have convenient to organize them this way. So I take n to be greater than or equal to m. We have an isomorphism of 3 of these algebras as one parameter, DOAs. And there's a nice relationship between the levels. So this is a xi, this is a 1 over xi, and this xi prime satisfies this nice relationship, which also appeared in Thomas's talk. Okay. So this was conjectured in the physics literature several years ago. And I want to explain how the two dualities I mentioned before, Figgen-Frankel duality and the coset realization, are extremal cases of this. Thomas talked about a slightly less trivial case, which I won't mention again. Okay, so the case of d xi n0. So n0 means that there's no trivial block. That's just the W algebra of SLN. And same thing for c xi of n0. That's also just W algebra.
Because it's only in this for SLN duality, not for arbitrary.
Only SLN. Yeah, this is only type A, which I'm talking about now. Yeah, there are similar statements for other types that I.
Not exceptional.
Not exceptional. Yeah, only the classical types. So this is yeah. So this doesn't recover Frege-Frenkel duality in full generality. It recovers it in type A. Yeah, that's right. So yeah, and you see that this relationship between the levels, that xi and xi inverse, this is the relation given by Frege-Frenkel duality. So this whole family of isomorphisms that I had in the previous slide, where the relationship between the levels is that one's the inverse of the other. I think of these as a natural generalization of Frege-Frenkel duality. So it's not a duality between full W algebra, it's only between, it's an isomorphism of the affine cosets. And so the other ones they should be thought of as some generalization. What's interesting is that once you go away from n equals 0, the duality is between a W algebra and a W superalgebra. So it's always between a superalgebra always appears in it. Okay, so I claim that the other one, if I take n equals 0, the one that switches the n and m when one of them is a 0, this is the coset realization. So from the previous slide, the case where this first component was a 0, this was defined slightly differently. It's not a W algebra. It's this tensor product of an affine times a fermion algebra. And it has this diagonal embedding because the fermion algebra has an action. Well, it has an action of L1 SLN, but also there's a Heisenberg, so I should have said L1 GLN. And so, yeah, this should be a GLN, actually. So yeah, so when I take this this coset, this is a GLN, but I can pass to an SLN here, and F2N is an extension of L1 SLN. So it actually doesn't matter if you replace this with L1 SLN, and then the Heisenberg will go away. And this is exactly the formula for the coset realization in type A. So this much larger family, where these can be whatever numbers I want, I think of this as a generalization of, these are all isomorphisms of coset realization type. Okay, so let me say a few words about how such things were proven, and then I'll say a few things about why this might be interesting. So the mechanism is that I want to first describe the generating types of these algebras. So there's a mechanism for doing this where I pass to the large level limit. So there's a general fact about W algebras associated with, the Lie superalgebra is simple, has an invariant, non-degenerate, supersymmetric bilinear form. There's a way of taking a free field, there's a way of taking a limit which is a simple free field algebra. And the strong generating type of the coset that I was interested in is the same as the strong generating type of the orbifold, which is an easier problem. So if I apply this general procedure in this situation, I can use classical invariant theory to find the generating type. So the statement is that the C-xi NM has this generating type. So it's of type 2, 3 up to something. What that means is that there's one field in weight 2, one field in weight 3, all the way up to one field in this particular weight. Those things close non-linearly under ODE. And they form not a PBW basis, but the monomials in those form a spanning set. And there's a similar description for the Ds, except that you don't go quite as far. Okay, so in fact, the invariant theory which is relevant is simply the Weil's first and second fundamental theorems of invariant theory for the standard representation of GLN. So anyway, so you're able to describe the generating type. So showing that such algebras are isomorphic directly is impossible because we don't know, even WSLN, we don't have closed formulas for all the OPEs. So we need some more indirect way of showing that such things are isomorphic. So there's a way of, it turns out that you can classify VOAs with this generating type. And when I say classify, that means that they come from a universal object. So this is one reason why such universal objects can be useful, so they serve as classifying objects for VOAs with some prescribed generating type. So there is such an object, so I denoted it by WC lambda in my paper, but it appears in physics literature and other papers with different notation. But what it is it's a large VOA which has generating type 2, 3 all the way out. So it has infinitely many strong generators. It's freely generated at this type. So the universal one actually does have a PBW basis. And it's defined over the polynomial ring in two variables. So C is the central charge, lambda is some other variable that I chose to call lambda for no particular reason. And this VOA is of CFT type, and the weight 0 component is, instead of being the complex numbers, is just identified with this ring. The whole thing is a free module over this ring. Okay, and so when I say that it's universal, that means that there's no such VOA that has more than 2 parameters in a non-trivial way. I can always tensor this VOA with some ring with as many parameters as I want, but I don't get new isomorphism types of VOAs of this form. So there's exactly a 2-dimensional moduli space of VOAs of this type. And not all of them are distinct, but most of them are. So if the central charge is 0, then it doesn't matter. If you pass to the simple one, then they're all the same. And also if the central charge is -2, if you pass to the simple one, then you get in all cases. It doesn't matter what the lambda is, you always get this similar algebra, the algebra of C equals -2. But aside from those degeneracies, there's a bijection between points in the plane, which is the parameter space, and VOAs with this generating type. Okay, so this thing has infinitely many generators, but I'm looking for ones that only stop at some point. So it turns out that this stopping at some point you can control, because when for certain values of the parameters you require a singular vector that allows the field in one conformal weight higher to decouple, and then all the higher ones do as well. So this is how you get VOAs of this type. And I should say that the way this is constructed is I have to construct a certain nonlinear Lie conformal algebra. So there's a paper of Victor Katz and Alberto de Sol from quite a long time ago, which is a very foundational paper in the subject. It basically tells you that just like in ring theory, you can construct VOAs via generators and relations. So we, in an essential way, we use the results of that paper to do this construction.
Is C just like the central charge of the Virasoro?
Yes.
Is there any?
There's no particular meaning that it has. So there is another parameter that appears somewhere in the OPE algebra. Most authors who've worked with the structure take the other parameter to be n, so that when you set it to be n being a free parameter, but when I set it to be a positive integer, then the simple quotient is WSLN. But for some reasons, well, that's a good choice, but from the perspective of constructing the algebra, it's not an optimal way to do it. But even the one that I chose is not fully canonical, but my choice is such that the algebra is defined over the ring of polynomials rather than rational functions. I have some reason to prefer polynomials to rational functions, and even then you have some choices. This is the one that makes things look as simple as possible given all my other constraints. So the approach is optimized for the purpose of showing that this exists. And the OPE algebra is quite complicated, but there's a certain recursive property that you can use to show that it exists that's easier to handle with these parameters. Okay.
So you're saying that you can classify all W algebras freely generated by fields of conformal weight 2, 3, etc. n.
No. So VOAs that have that particular generating type, 2, 3 up to something, those are all classified. Most of them are not free.
I'm saying which are generated by
Yes.
this you can classify.
Yeah. Well, they're all quotients of this universal one, but how explicitly can you realize them? So the ones that appear in this talk, very explicit.
How to build this quotient?
There's many things I don't know
is
about.
not clear. Okay.
No. I mean, I have a list of, maybe I'll say a little bit more and then I'll come back and I'll say something. But I should say that they're mostly not freely generated. So the only quotients of this that, at least on the list that we have that are freely generated are WSLNs. All the other ones have relations. Okay. So, sorry, I think I'm trying to go backwards, but I'm going. Okay, yeah, so here. So let me say a few more words about this. So how do you get quotients of this algebra? So a reasonable way to think of quotients of this is consider an ideal in the ring of functions, which is, this is the weight 0 space, but I also think of it as defined over this ring. And I can consider the VOA ideal. Sorry, so I times this W is the VOA ideal generated by I. If I think of it as a component of weight 0, then it's meaningful to talk about this VOA. This is just the set of I linear combinations of elements of this. So I can take this quotient. And so when I do this quotient, then in weight 0, I obtain this quotient ring. I can think of this as being a VOA over the quotient ring, which is some one parameter ring if I choose coordinates. So this thing will still have the same graded character as the original WC lambda. And if I choose this I arbitrarily, if I pick a generic I, this will be simple. So in a meaningful sense, WC lambda is simple. You have to define being simple over a ring. It's equivalent to saying that for generic points in the parameter space, the VOA is simple. And also for generic ideals, this will be simple. But then there are certain special ideals where it's not simple. So as a one-parameter VOA, there will be a singular vector and some conformal weight, and then you can take the quotient by the maximal proper graded ideal. So certain special ones, I can do this, and then W lower I is the simple graded quotient. These are the ones that are operative in this talk. These are the ones that can truncate to something with finitely many generating fields. And so there's a statement that all simple one-parameter VOAs of this type satisfying some hypotheses. So these hypotheses in practice are easy to check, so this is not this doesn't cause too many problems. They will arise in this form. And so I'm going to give a name to this corresponding variety for the truncation curve. So these are some curve in the plane. So these curves for all the known ideals can be computed explicitly, and they have some nice properties.
What is the one parameter of VOA? Is something parameter of central charge, or?
You can think of this in a coordinate-free way if you prefer. So this is a polynomial in two variables. If I quotient by a prime ideal, this will typically be a ring with curl dimension 1. So I can choose a parametrization of this ring. Then I get I can choose a parametrization of the variety, and I get a one-parameter family. So I will typically use, I don't write any formulas in this talk, but I use the shifted level as the parameter. The formulas are nicest if you level, but you have many choices of parameters. And there's a way of thinking of all these things in a coordinate-free way, which I have not written. Maybe it's useful. I can tell you more about it if you want. Okay, but that's the reason this is a one-parameter VOA is because this is a ring with curl dimension 1. Okay, so these algebras, we use some invariant theory to describe their generating types. They have this form by virtue of this being a universal object. And so we can calculate the explicit curves. So how do you do this? I know that this W algebra exists. I know that it's an extension of an affine times some quotient of this algebra. So let's say I don't know what this I is, but I know that these C's and D's are of this form. So there exists some I. And the extension is generated by these fields, these off-diagonal fields that could be even or odd depending on whether I'm working with a C or a D. They have a fixed conformal weight, and they have a fixed transformation under GLM. So it turns out that this information uniquely and explicitly determines I. Simply using the existence of this W algebra and doing some OPE calculations, I have to impose some Jacobi identities, look at what possible OPE algebras can occur, and then impose some constraints from VOA axioms. You get a formula for this lambda parameter, so you can completely determine I. And this procedure is independent of N and M. Yeah.
To get C and D from WI, do you have to evaluate the parameter to some particular value?
No. So C and D. You impose one functional relation between lambda and C. So you can think of it this way. There's some ideal that you impose that you compute explicitly. The formula for it in terms of C and lambda is very complicated. It's better to parametrize, and then you get a nicer formula. It's better to write it in terms of the shifted level. But anyway, you can compute these ideals, and so it works equally well for the C's and D's, and the triality theorem follows the explicit form of these ideals. There's a symmetry of these ideals that produce triality. Okay, so this is how you prove such statements. So there's a lot of things that one can do with these results. So some of them were, Thomas mentioned in his talk. These trialities are useful for representation theory because there's some relationships between representations of superalgebras and ordinary algebras. Actually, for Fagan-Frankel type trialities, there's a way of creating the isomorphism of affine cosets to a functor that takes modules for a hook type algebra and gives you modules for the corresponding Fagan-Frankel dual W algebra, W superalgebra. So I'm not going to talk more about representation theoretic applications here. There may be one more thing I should say is that these truncation curves they're nice curves in the plane. You can compute their intersection points. It turns out all the intersection points are rational points, when two curves intersect, that means that two of these VOAs, which generically are quite different, at that point their simple quotients are isomorphic. So you get an isomorphism between algebras that are not obviously related. Some of these isomorphisms are previously known, and this gives many more, and it gives a conceptual explanation for them. So for example, the parafermion algebra of SL2, this is the coset of Heisenberg inside SL2. This is some algebra with generating type 2, 3, 4, 5. So when the level is a positive integer, k, that's isomorphic to the W algebra of SLK. This is a result of Arakawa, Lam, and Yamada. And this is, those isomorphisms correspond to intersection curves. Okay, so the real reason why I'm interested in these algebras is not so much that, what I just said, but that there's an expectation that these algebras are building blocks of all the W superalgebras of type A. And so I should have said that these C's and D's, these are the Y algebras of Gayoto and Rabchuk. I mean, you have to tensor with a Heisenberg algebra, and then they become these Y algebras. So these are, there's some expectation that these are building blocks. And so W algebras for non-principal equivalents are much more complicated. We don't have as good understanding as we do for these basic cases. But in some sense, you can build them up from these baby ones. This is the more. When I say building blocks, I mean that you can realize these other W algebras as extensions of tensor products of some number of copies of these with prescribed parameters, and maybe you have to throw in some Heisenberg algebras as well. Okay, so let me give a couple of examples of things like this that we expect, these are not proven yet. Let's say that n is bigger than m, and they're all at least 2. Let me look at the two-column partition, where I have a column of height n, and a column of height m, which is the smaller one. Okay, so this W algebra we expect to be an extension of 2 of these C algebras. Because the C's are the same as the D's under triality, I'm only going to work with the C algebras now. So which ones are they? So CNM means that instead of having this block which has 2 columns, I just make the M column, I sort of turn it by 90 degrees, I make it a bunch of trivial ones. So this CNM, there's an F and GLM, and then I take the coset, I get this algebra. And then what it should be tensored with is a CM0, which is just a W algebra, principal W algebra of SLM. For some psi prime, which I didn't write down, but it's easy to find the formula for this. So in particular, there should be an embedding of this principal W algebra. And there's some reasons why we expect this. And it's, Thomas mentioned this a little bit, that you can do the reduction first along the nilpotent with one block, and if you choose the order correctly, then there's some reason to expect this, but it's not easy at all to see this directly from the definition of the W algebras. So we think that there's such an embedding, and then there's a lot of interesting questions you can ask if this is true. So there's been a lot of studies by Victor Katz and Adamovich and various people on conformal embeddings. So you have a W algebra has an affine subalgebra. For which levels does the VOA collapse to its affine algebra? Or if it doesn't collapse, then when is the affine one conformally embedded, and when do you have a non-trivial extension? So these results are useful, and there's many more questions of this nature that one can ask. Not only do W algebras sometimes collapse to an affine subalgebra, they can also collapse to a smaller W algebra. It's interesting to try to find such levels. That probably has applications in representation theory as well. And I know some examples of this, so it's the general results of this we don't have yet. Maybe I should mention too that if you throw in a tail, so if you take SLN plus M plus R, where you have some big, and you take the same nilpotent, it just lives in this SLN plus M block of larger type A algebra, then you, the affine, this thing will have a GLR as a subalgebra. But then you should also, this should just be replaced by M plus R, and then this 0 should be replaced by an R. A similar story. So I said something about 2 unequal columns, but there's also an iterative procedure for saying what happens if you have as many columns as you want. The number of these C algebras that will appear should be equal to the number of columns. Okay. So now, what about columns that are the same height? So let's look at the, so this is a rectangular W algebra. So n to the m just means m blocks of size n. So this is one of these rectangular nilpotents inside SLNM. this rectangular W algebra, now I have M columns. They're all the same height that we expect it to be. There's an extra rank M Heisenberg algebra that will appear, but it should be an extension of a product of this and a bunch of these where they go like N, Jn. Okay. And maybe I'll mention one more example. So this is the example from Linshaw talk. So this is the principal W algebra of SL n plus 1n. So this is, so from her perspective, this was a supersymmetric W algebra. But you can also just extract the ordinary vertex superalgebra, just separate the superfield and take whatever you get. So this has n equals 2 supersymmetry. And this is something that belongs in our formalism. I said W, the C's are building blocks for type A. I also meant W superalgebras of type A. So what I expected, this is an extension of a Heisenberg times a C1n. C1n is just the coset of a GLN inside SLN plus 1, because the principal block, there is no principal block. This is just a coset of an affine algebra. And then Cn0 is a principal W algebra. So this is what one expects. And there's actually a precise conjecture that goes back to Ito from the physics literature a long time ago that says not only is it an extension like this, but we actually have a coset realization of this principal W superalgebra. And so the way it goes is that you take affine SLN plus 1 and I tensor it with 2n fermions. Sitting inside affine SLN plus 1 is, of course, affine SLN. So this GLN embeds diagonally, first of all, in this upper block here, and then it also acts on these fermions, and I could consider this coset. So why do I say that this is more precise? Well, from this perspective, it's obvious that this coset is manifestly an extension of algebras like this, because if you look at the part where you replace this with GLN, then that's the coset realization of this copy on the nose. And if you sitting inside this coset will also be the stuff that has no fermions in it. You just look at the coset of this algebra inside here. That's exactly C1n. And there's an extra Heisenberg algebra. So this, I think, is quite an interesting thing to prove. And it also, you can think of this as a type of triality for these superalgebras. And also, I expect this to be one large family, which one can write down, but we can't prove anything, even this one. So the case when n is 1 is well known because you can. This is just a Heisenberg coset, and both sides are just the n equals 2 superconformal algebra. But the first non-trivial case, Naoki and I have a conference proceedings paper where we worked this out for the case of SL3/2. So this is true. Okay. So let me say something very quick about the orthosymplectic setting. So there's a similar story that goes through more or less the same way. The only thing is that there's more types and it's more complicated to write it down. So there's, instead of being just 2 types, there's 8 types of Lie superalgebras of these types. And so these are what we call orthosymplectic hook type. And so the property that they have is that, first of all, there's a decomposition as some pair of Lie subalgebras or superalgebras A and B, and then everything else is a tensor product of the standard times the standard representation. Okay, so B has to be either type B or type C. This A, there are 4 choices for what it can be. And so for each choice of B and A, there's exactly one Lie superalgebra where this is realized. That's why we get 8. Okay, and so we do the same thing that we did before. We take the nilpotent, which is principal in the B block, which is either a B or a C, and trivial in the A block. And then we get a VOA, we take the affine coset. And as I said before, we sometimes have to take a Z2 invariant space. That's when the A is either orthogonal or OSP. So we get something, again, you can use classical invariant theory to determine the strong generating type, and it's always of type W246 up to some point. So algebras of this kind are also classified by some universal algebra. And this I constructed with Shishink Kanade a couple of years ago. And it's also a 2-parameter algebra. And all these algebras have truncation curves. You can compute them, and you can find all the trialities. They belong in 4 families, so the statement is more complicated. And special cases of these trialities include Fagan-Frankel duality for types B, C, D, and OSP 1, 2n, and also all the coset realizations that we have in these types, and then there's many more. And also all the trialities are either of coset realization type or Fagan-Frankel type, just like before. Okay. And they have applications too. You can intersect truncation curves and you can find interesting coincidences. Using these coincidences, you also deduce some new rationality results for W algebras. But what's really interesting is whether these algebras can serve as building blocks for orthosymplectic W algebras. And the answer is no. It's not enough to serve as building blocks. So the question that motivates what I actually wanted to talk about today is what else do you need conjecturally to serve as building blocks? So,
I have a quick question.
yeah.
But this is like the case, like, there's like the Lie algebra A that, it's the centralizer thing, but then, typically the corresponding group is like disconnected. And so do the components of those groups across the trialities, is there some nice?
You mean the component group for the Lie algebra A?
Or like, if you actually took if you took the centralizer of that SL2 in the group, like its Lie algebra is this A, and then like you also.
Yeah. Oh, so you mean which group do you? So A is the centralizer of this Lie algebra. That's correct. When I take coset of this thing, yes, I have to take the orbifold is exactly the quotient of the component group, the connected group. Yeah. That's the reason for this. So it's only a Z2 that appears here that I have to do. Yeah. If you only take the coset, then that doesn't quite work, because then when you take invariance, if the coset is something orthogonal, then when you take coset, this will turn into some invariant theory problem. But invariant theory of the orthogonal group, you get some determinants, some things of high degree which you don't want. You take Z2 invariance, they go away. Same thing for OSP invariance. Okay. Yeah. We also need the classical invariant theory of OSP 1, 2, n. Okay. So the difficulty here is that these even spin algebras are not enough to be building blocks. And so an easy way of seeing that is I want to give a slightly different interpretation of the ones that we know. So the WC lambda, the way that I described it before, is some kind of unifying object for these SLNW algebras. But you can think of it just as well as a unifying object for these affine cosets of type A inside one bigger type A, GLN inside SLN plus 1. And so these cosets they belong in this family, and the OPE algebra, if you choose generators carefully, is given by rational functions of n. So it's meaningful to analytically continue this variable n. That could be your choice of second parameter rather than lambda. So this is one way of constructing this unifying family. And then the even spin algebra, you can also, I was talking about it before as a unifying family for type C or B principal W algebras, but it's just as good to think of it as a unifying family for these orthogonal cosets and SON inside one bigger. So it doesn't matter whether this is even or odd. This family of cosets, again, I have to take the Z2 invariance and get rid of these extra determinants, but this is some algebra of type 2, 3, 4, et cetera. These analytically continue. Okay? So these are other ways of thinking about these universal families. And I can say, what if I consider the same structure in type C? So I look at the coset of SP, this should say 2n, that's a typo, but SP2n inside SP2n plus 2, one higher rank symplectic Lie algebra. So this family, it turns out, well, the generating type is a little bit more complicated because one thing that you know is that there's an SP2 which commutes with SP2n. So there's at least 3 fields in weight 1. So this can't possibly be of the type that I was considering before. And again, you can figure out what the generating type is using invariant theory of the symplectic group. It's not that difficult to see that all these cosets have this form. So there's 1 to the 3 means 3 fields in weight 1. That's my affine SP2. There's going to be 1 field in each even weight and then 3 fields in each odd weight. And the 3 fields, these will transform as the adjoint under SP2, and the even ones will be SP2 trivial. So this thing for a fixed choice of n will terminate at some point, but that where it terminates gets further and further out depending on what n is, and the unifying object is freely generated of this type. Okay, so it's not that difficult to see that there exists a 2-parameter freely generated VOA of this type, where the parameters can be taken to be k and n. But what is very difficult and is not proven yet, but we expect it, is that actually is the universal one. So the biggest algebra of this type really only has 2 parameters. So to prove that is necessary to do anything interesting with this algebra. So, but the two things are manifestly clear is that there is a two-parameter really like this. And there also exists a universal one. We just don't know how many parameters it has. Okay, so what student Vlad has been working on for a while and is almost done with, modulo some finite computer calculation, is to prove that the universal one has two parameters. Okay, so everything I'm going to say after this, well, not everything, but interesting applications depend on whether this can be proven completely. I'm going to denote this by WSP2. And in his formulation, the parameters are the central charge of the affine and the level K of the SP2. Again, you have different choices. That's a convenient choice of parameters. And so the idea of the construction is similar to the construction of this algebra, the type A one and the even spin one, but it's a lot more involved. So what you have to do is try to look at the most general OPE algebra with the prescribed generating type and also the action of the SP2 on the extra fields. So I postulate that you have some fields, you have these ones that are in odd weights that transform as this adjoint representation. I can make some simplifying assumptions, which I also did in the previous papers, where define higher fields as descendants of earlier ones. This makes the OPE calculations more tractable. So we try to write down the most general thing, and then there's a lot of identities that have to be satisfied, and that gives us some algebraic equations and the structure constants. Some of them are linear, some of them are non-linear. There's some preferred order for solving these, and a priori this is infinitely many equations and infinitely many variables. It's not obvious that the procedure will terminate, but it does, and it terminates after weight 15. That was similar to the previous problem. So the first step is showing that this turns into a finite problem, and you have to deal with the finite problem. So this is still work in progress. Okay, so this thing that I wrote down, it may seem somewhat random. I tried to motivate it by looking at these cosets in type C. But there's actually a lot of VOAs that have this generating type. So let me tell you a little bit about some examples. There's 8 families of them. It's very similar to the story of even spin algebras. So let me tell you about a few and then explain how you can get the other 8 families from these. So let's start with SO4N. N should be at least 2. And this has a decomposition. So it has a copy of SP2N and then a commuting copy of SP2. And then it has some other stuff that transforms in this way as a module for SP2N plus SP2. So the SP2 part is the adjoint representation, and then there's this rho omega 2, which is one piece of the second exterior power of the standard representation. Okay, and so what I want to do is take the nilpotent in G, which is, I'm going to call it FSP2N because it's simply the nilpotent in this thing, which is sitting inside SP2N as the principal nilpotent. Okay, and so I can think of this corresponding W algebra as being an analog of the rectangular W algebras, where this is the rectangular W algebra in type A, where I had M blocks of this size. So this GLN is playing the role of SP2N. This is where I have my principal block. And this, what I call the rectangular part, there is a GLM here, which commutes with it centralizes the SL2. This thing is replaced by SP2, so it's only rectangular in a small way. So it's the analog of this. And then so you can read off what the generating type of this W algebra is from this decomposition. So the SP2 gives you these 3 fields. Those are, they commute with this nilpotent. The fields in weights 2, 4 up to 2n, that comes from the principal block. And then all these collections of odd fields, they come from the decomposition of rho omega 2. You have 3 of them because this is tensored with C3. So you have this kind of description of the W algebra. Okay, so, and then there's a similar one where I take G to be symplectic rather than orthogonal. I take it to be SP2 times 2n plus 1. And this has an SO2n plus 1. And I have a decomposition. This has a commuting SP2, and you have a similar looking decomposition. And, you know, this. Yeah, so the way that this module arises is not the second exterior power, it's the second symmetric power of the standard representation of this B-type algebra. And I I take the nilpotent, which is principal here inside this SO2n plus 1. And again, this is some kind of analog of rectangular W algebras. And I've just switched the role of B and C. And you have a similar description of the generating type. So even though this has freely generated the same generating type, this is not isomorphic to the other. It's something else. Okay, but these are examples of VOAs with this type that will be quotients of the universal VOA of this type. Once you understand these, you see that you can cook up a bunch more families in a formal way, which is similar to what we did for the orthosymplectic setting. So we can consider W algebras where you have that type of nilpotent, but then you have some tail, which is a big We algebra that commutes with the SL2 triple. And then you have to take a coset by this tail algebra, and then you get something of the same generating type. Okay, so I can replace my, anyway, so there's a formal way of doing this. My principal part, I have two choices. It's either B or C. My rectangular part is always going to be SP2. And then this tail algebra, there are 4 choices. And then there's a total of 8 possibilities. Each one of them, there's one Lie superalgebra that does the job. This is my 8 families. So here's an example. It's kind of the easiest one where I just take SO4n plus 2r, and this would be my tail algebra. So I take SP2n to be the same nilpotent that I wrote down in here. It's principal inside this SP2n. So this W algebra, it now has this tail algebra coming from an SO2r. These 2 levels, there's some formula for it. I have to take the coset of the tail algebra, and then because this is an orthogonal algebra, I have to take Z2 orbifold. I get something which has the correct generating type. It's not freely generated anymore, but has this generating type, therefore it's the quotient of this universal object. These statements don't depend on having not finished the proof of this being 2 parameters. These are always going to be quotients of whatever this universal object is. Okay, so that's how I get a bunch of these families. So these I think of as the type C analogs of Guyot-Rabchuk algebras. So they're a little bit more complicated, but there's the same quantity of them. There's 8 n by m, 8 families that are each parameterized by 2 positive integers. And so even using the partial OPE algebra that Vlad is working with, he's already able to compute their truncation curves. So he knows what the curves are for each of these. And then we need to know that the algebra has 2 parameters to be able to argue that when when 2 truncation curves intersect, we have isomorphism of algebras. That kind of result depends on there being a bijection between quotients and truncation curves. So anyway, just like the previous situations, the intersection points are nice. They're always rational points. You get interesting coincidences. And the expectation that we have is that the even spin quotients, the orthosymplectic Y algebras, were not enough to be building blocks, but if you take these guys and then these 8 families, this will be enough to be building blocks for all the orthosymplectic W superalgebras. I should mention a few things. So one thing which is, we were hoping to find some trialities in this family, but we don't, and maybe in retrospect that's what you would expect because of the presence of this affine subalgebra. All all algebras in these 8 families are distinct as one-parameter algebras. There are many pointwise coincidences, but there are no one-parameter coincidences. And the other thing which is interesting is that this is an open question, but I think it's well expected that all the finitely generated quotients of these algebras are the ones that I wrote down, not in my talk, but in our papers, the ones that physicists conjectured and were able to compute, namely the Y algebras, the CNMs, and then similar things here. We don't expect there to be more finite truncations of those algebras. But these 8 families are not all the interesting truncations of this WC lambda. So I only have a few minutes left, so I'll be very sketchy here, but let me explain why there should be more, where they come from, and this is something which you don't see in these types precisely because they have no affine subalgebra, and then like why are these other ones interesting? Okay, so I have to take a step back and talk about something totally different. Let me talk about diagonal cosets in type C. Okay, so let's consider 4K fermions. You can think of this as 2K copies of the BC system. And so this is well known that it has a copy of L1 sp2k and also LK sp2 which form a dual pair. That means that the commuton of one equals the other and vice versa. So the tensor product of these formally embeds in this fermion algebra. And using this fact, I can consider a diagonal coset, where what I do is I take SP2K at level L-1, and then this one has an action of L1 SP2K. So there's a diagonal action of VL SP2K in this product, and I can consider the coset. Okay. Notice that there's a piece of this coset which just doesn't involve any of these algebras. It's simply the component that lives in the fermion algebra, and LK SP2 lives in the fermion algebra. So one thing which manifestly lives in this coset is this copy of LK SP2. This, mind you, is the simple LK SP2. Okay? So it's easy to compute the strong generating type of this diagonal coset. We do the usual thing where we pass to the large level limit. The large level limit, these affine things go away. It's just the SP2K orbifold of 4K fermions. I can use invariant theory to deduce this. It has this generating type. Therefore, this is a quotient. It's a one-parameter quotient of the parameter being the level L. One-parameter quotient of my universal algebra of this type, with the property that this K is fixed. Like, unlike those 8 families that I wrote down where this K varies, this K is fixed, and it's the simple affine that lives in there. So for each positive integer K, there exists a quotient of my universal algebra where L1K embeds and K is fixed. There's no analog of these cosets in the previous stories. Okay, so I'm a little bit short on time, but let me say a few words about this. So one can check that this seq LK is an extension of the product of 2 universal W algebras of SP2K. So this K, the level of my SL2, SP2, determines which, what rank these W algebras appear. They have this formula. This is something that was...
corresponding to principal method.
That's right. Yeah, these are principal ones. Right. So the way that we know this is that this is known when L is a positive integer, and then it holds at enough points that we can deduce it for the family. And these are now the universal ones. So you might think that that means that the universal, so this means that these guys are extensions of 2 even spin algebras. So you might think that this implies that this universal object itself is an extension of 2 even spin algebras. That's not true. It's most certainly not. But when you pass to this quotient where K is an integer, and you pass to the simple quotient where this thing becomes simple, then it is. Okay, so after doing this procedure, this thing really is in some trouble with this now. I think it's not working anymore. Okay, there it goes. Okay, so I'm almost out of time, but let me just say a few words. So if L-1 is admissible for SP2K, then this embedding of the diagonal embedding descends to an embedding of simple quotients. And you can consider this coset. This coset also will be the simple quotient of this universal one. This comes from a general fact about such cosets, simply because this level is the shifted level is positive. That kind of statement is always true. And so this is a conjecture. We conjecture that when, if I choose my levels such that, so K is my fixed positive integer. I choose L so that L-1 is admissible, and the levels of these guys are non-degenerate admissibles. Therefore, these W algebras are rational ones. Well, we think that the simple rational ones should be there, and that these cosets should be least irrational. So why do we make this conjecture? This is by analogy with the diagonal cosets in type in ADE types. It's a very similar statement, and we know that that's true there because the coset is a W algebra, which is simple and it's not degenerate admissible level. So this is a conjectural, like, large bucket of rational VOAs that are that come from this universal family. Okay, I'm out of time. I was going to give you an example of why this is useful. Let me just say it in a moment in words. The existence of all these maybe rational algebras that come from this universal one allows you to prove, if we can prove everything, new rationality results for W superalgebras. So you can find some families of some W algebra where the affine algebra is, has positive integer level. And it's either the SP2 with some positive integer level k, and then the other, is whatever this tail algebra is also positive integer level. Such that the affine coset, well, it lives in some truncation curve for that W algebra, but it's coincident with the truncation curve for this algebra. That means that you have an isomorphism of simple cosets. And so if these are rational, then the original W algebra you can see as an extension of rational algebras. So there are many examples like this of W superalgebras that we can't prove this yet because we haven't shown that this algebra has two parameters, but we expect they're rational from this perspective.